Good morning, everybody. How are you? Uh, this section is about Math 127. And it's covering week 6 and week 7. And the lecture notes you will see in your LMS, they cover chapter 6 ABC lecture notes. Our lecture today and the next two sessions will be concentrating on how to use derivatives. You know, derivatives can be used a lot everywhere in engineering. That's the most important thing in any course from the first semester until the fourth year of your degree. So one of the applications we're going to use today, it's how to graph a simple function. I know in Math 116, you've learned linear function, quadratic function, trigonometric function, exponential function, reciprocal functions. All these functions, you learn their properties. Today, and the next two sessions, we will only focus on polynomials. When we mean polynomials, means any x to the power 2, power 1, power cubed, power 4, power 5, blah, blah, blah. Okay, so these are the ones we're going to be using. But before we go to this, we need to make sure that we are so good with derivatives, especially when I ask you, what is the derivative of x to the power 3? You should quickly say, by using the limit, limit is finished, using the power rule, it's going to be bring the 3 down and minus the power by 1. So it's going to be 3x squared. I hope you remember that, because that's the most important thing. That's number one. So before we start with all of this, I just want to thank my son, who's trying to help me in everything I do, especially in the technology part. And I want to thank very much our administration, especially Mrs. Dunya, Mr. Professor Dr. Hussein, and our Dr. Ma'moon for their positive support and technology. Now, before we start with all of this, we have in Math 1 something called gradient and slope. You remember that thing? Quick revision. When I go this way, a straight line goes up. I'm going uphill. Let's think about it going uphill. When you go that way, the slope of this street, of this line, is called M. That's either called slope or it's called gradient. In this situation, it's always positive. All right? Now we need to keep this in mind all the time. While if I am going uphill, there's always thing going up, but I am turning to the left, the slope of this line is always negative. And if I'm standing on a straight line like this, and this straight line has no slope, flat, horizontal, then the slope of this is also neither positive nor negative. All right, we call it 0. And in the previous chapters, we said that the first derivative with respect to f, or dy dx, are actually different labels for the gradient. Okay, just keep this in mind. And if you go to any physics or engineering, they will call these rate of change. When we say rate of change, means speed change with respect to time, acceleration with respect to time. Maybe in thermodynamics, we call it heat changes with respect to time. If you talk about physics, volumes change with respect to time. So anything has to do with time or with temperature. So sometimes we give it different labeling. dq, dt. Could be time or temperature. Could be dv over dt or dr, or whatever you wish. Maybe the rate of change of volume with respect to its radius. So anyway, all these expressions depends on the derivative. So what can we do to this? How can we use them properly? Now, I'm going to show you a sketch. This sketch of a curve, you have the x-axis and you have the y-axis, and that's your origin. All right, I'm going to draw a simple function. I know it's called cubic function. This function has an equation of y. What distinguishes this function? What does it look like about it? It crosses the x-axis somewhere here. Maybe later on, it's crossing the y-axis somewhere here. And we took those before. What happens when you cross the x-axis? The y equal to 0. What happens when you cross the y-axis? The x equals 0. And we can use your calculator for solving mode 5.3, mode 5.4. We already know these things from math 1. Now, the most important thing what distinguishes this function is the top point in the top, and the bottom point. And there is some hidden point, you don't know where is it. When you go down and suddenly you change the concavity of this, look, somewhere here, I'm not sure, and that point has a name. All these points are called turning points. Turning points. I want to discuss these turning points. I want to talk about little basics, so when we go next time, we know what to do, how to solve questions. Turning points are two types. First type is called stationary points. And there's another type called non-stationary points. All right? So when you throw a stone all the way up, it goes all the way up, then suddenly stop and then comes down. That's called stationary. Station. It stops in air for a matter of milliseconds. Those stationary points, there are three types of stationary points. One is called a maximum point, okay? One, it's also called a minimum point, and a third one called an inflection point. All right? Some people, or we can still call stationary point called critical points. All right? Now, what distinguishes these points? What distinguishes these points that the gradient of these points is always what? The first derivative. Remember, first derivative means what? The gradient. If I'm looking to find any of these points, simply, this is your game. Take this derivative and equal that to 0. That's the secret. And solve. So, do the derivative of this, whatever function you have, and then equal it to 0, and you can find any stationary values. But what's the maximum? If you go all the way up, you stop somewhere and you go down. Isn't that a peak of a mountain? The highest point, the greatest point, the largest point, maximum profit you can make in your company? So, what's happening here? If I draw a tangent here, wouldn't that tangent be positive or negative gradient? We just talked about a minute. This is positive, slope. So any place here, when you are 6, 5, 4, 3, 2, 1, until here, you got a 0. Isn't the slope 0 at the highest point? Yes. So if I want to find the highest point, just take the gradient, equal it to 0. And we said before, gradient means derivative, first derivative only. And then what's happening? The gradient will go -1, -2, -3, -7, -100. So that's how the gradient changes. So whenever you go from positive, passing through 0, and then going back to negative slope, that's the definition of a maximum point. How about a minimum point? Ta-da! You go all the way, you're doing some scuba diving, you get to the lowest point in the sea, and then you go up. So what's happening here? If you draw a tangent at any point on this part, the gradient or the slope or the derivative will be always negative. So this -5, -4, -3, -2, -0.9, and then the lowest point has a derivative of 0. Got it so far? And then coming back, you want to ascend, you want to go up, take some air, because you are at the least point in the sea. So +1, +2, +3, because any line here has a positive slope. That's cool. How about inflection point? An inflection point, when you go all the way up and you stop here, oh look, this is +5, +3, +1. Suddenly you are 0 at this point. So your third derivative is 0. And then you decided, I don't want to go back. Actually, I want to keep going up. Then you keep +1, +2, +5, positive whatever until. So when you go from positive values of a slope, passing through this point at a 0, then going up again, that's an inflection point. Likewise, there is another inflection point. When you go all the way down, you stop. I don't want to have, you go all the way down, you stop, and then you go down. So -5, -3, -2, -1. At this point, the tangent or the slope, the tangent line, its slope is 0, or the third derivative is 0. By the way, you forgot to show you that, and all of these ones, dy, dx, they all mean the same. So any notation you use for derivative is acceptable as far as you know what are you doing. So this is the derivative of y with respect to x. This is the third derivative of y. This is the third derivative of the function f or g or h. F is not short for a function. F is a name of a function. Anyway, all of these points, they have something in common. One thing in common. They all third derivative equal to 0 in order to find their stationary values. When I say stationary value, I simply mean, when I say stationary value, simply find x. That's all. Simple game. Nobody want to get smart. I will leave this for you. When you are at home, always go back to this, because this will show you the big picture. All right? So I need to clean. Before I clean that, why don't we review it again quickly? If I want to find any stationary point or any critical point, which I can call a turning point as well, take the first derivative. Hopefully you take it right. Any mistake, you finish. The whole question would be wrong. Once you take the first derivative, equate it to 0. So how can I solve it? I can go to mod 5.3, mod 5.4. But my advice to you, factorization, I know it's hard for some of you because you need to understand, but look at your lecture notes. Lecture note 6A, 6B, and 6C. We always show the factorization. If it happens you are short on time and you panic, please go to your mobile, to your calculator. All right? So remember, whenever you equate this to 0, you could get an inflection point, a minimum point, a maximum point. Very rarely you get an inflection point from the third derivative. There are special polynomial functions that you may get these. Now I'm going to clean that. Why? To show you what are the inflection points when it is non-stationary. You think I wrote inflection wrong. Actually, it has two ways to write it down. When you are driving an F-15 in the air, you cannot stop F-15 in the air to get some gas. So what's happening? Another plane will bring the gas to that plane, or this fighter plane in the sky, and they both go the same speed, same slope, in order to have some gas. Yeah, you've seen these movies before. So means, when we say non-stationary, means it doesn't stop. It means the first derivative, for your information, is not zero anymore. Uh-oh. Well, who's zero? If you conduct the second derivative, we can write it like this. I know I'm writing too much terminology, but it's good to remember because we've been away for a while. So if you do the second derivative and equate it to zero, you will find if there is an inflection point. Well, how does this inflection point look like? If you go all the way up and you stop and then you continue, guess what? When you draw a tangent at this point, you will notice what? This derivative is not equal to zero. This derivative is not equal to zero. So whether when you grade it is, let's say, plus 5, plus 4, plus 2, here probably plus 1.8, and suddenly go up again, plus 2, plus 3, plus 5. For example, so when you go from positive to the least point, and then keep up going positive. Or likewise, you're going all the way down to this point, and then you're going down. What's happening here? Let's say negative 5, negative 3, negative 1, and at this point, sorry, it's a negative 0.5, let's say. And then when you continue, negative 1, negative 2, negative blah, 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 blah. These points are called inflection points, but they are non-stationary points. They are called turning points. So you can see the difference now between a stationary point and non-stationary point. Okay? No slope is zero. Only if you want to find that, you just do the second derivative, okay, gentlemen, ladies, equal to zero. Once you do that, then you can find the inflection point. How can I tell that when I do this equal to zero, that I have an inflection point? How can I tell? Let me show you something with my red ink. What is happening here? You're going all the way up, all the way, as if you are concaving. So the curve is concaving down at this interval. Okay, suddenly at this point, the curve is concaving up. Uh-oh. So when there is a change in concavity, when there is a change, remember the word, change in concavity. Look at this one, concave down, this is called concave up. Look, it's concave up, all right? And suddenly at that point, you are concaving down. So when you go from concaving up to a certain, and then suddenly you're concaving down, or when you concave up, and at that point then you start to concave up, sorry, this is concave down. I hate colors a lot, but it's nice. When you concave down, suddenly you concave up, or when you concave up, at that point, which is called inflection point, concave down. That's the definition of inflection point. Not this inflection point, because this inflection point, if you know, when you go all the way to a zero slope, then you keep going. Look at that. It's positive, true, but zero, then positive. Here, no. Positive, less certain positive, but you keep going positive. To understand this better, the only way is to do an example, full example. Then why do we teach all of these? That's a good question. Since it's going to be our last 30 seconds, we do all of that to sketch an exact, a perfect curve. It's not enough to know the name of the properties like vertex. It's not enough to know this is called axisymmetry. It's also another technique to draw any polynomial function with the skills of graphing of derivatives. So, before we say bye-bye, remember, this is called second derivative. At that point, first of zero, still second derivative. and go all the way up. Look at this second derivative. So the second derivative here is equal to 0. All right? Now, the sign of the second derivative here is positives, and the sign of the second derivative here is negative. All right? And at this point, the slope is 0, but the second derivative has a value. The best way to see it, guys, ladies and gentlemen, it is simply, we should have an example next. So I will stop this video, and inshallah, let's call this chapter 6 and 7, part 1. The next video will be part 2. Thank you very much. Have a nice day. I know it's boom information, but when you see the second example, but remember, please, when you come next time, bring your calculator, bring your lecture notes. If you don't want it, it's okay, but bring pens and papers. Have a nice day.